So if you all can see the first initial slide and you have my audio, I'm going to go ahead and mute everybody. Once again, I will unmute the lines during certain portions of the session, the field questions, and I'll take questions at the end as well. So if there's no questions before we go, I'm going to go ahead and get started. The recording has started, so all attendees will receive the link to the recorded session.
All participants are now in listen-only mode.
So today we're going to talk about fiber characterization. What the heck is it? When do I have to do it? Why do I have to do it? What are the typical results? What are typical pass-fails? How we can get it done, etc. I'm a field engineer with JDSU. My name is Mike D. I've been with JDSU for 16.5 years. And this is our 4th fiber webinar. Zach Miller, one of our account managers, is hosting this. The 5th one will be on 100 gig and ROADM. So there will be a little bit of an overlap between 100 gig and this one. So we can take questions on 100 gig as it leads us into the next one. Historically, we've been doing these in about the 25th of the month, not on a Monday or a Friday. So look for invitation if 100 gig and ROADMs apply to you for about May 25th-ish. If we look at fiber deployments in the U.S., actually globally, and this is already a couple years old, the manufacturers of network connectors were making about 10 million a month. So all of us are getting more and more and more fiber into our networks. Even if we were a T1 copper POTS person, just about everybody is touching and involved with fiber now. One of the reasons for that is this slide here is already a couple years old. It's a little bit busy, but in 60 seconds globally, there's 168 million emails that are sent. I think half of them are from my company sometimes. 13,000 iPhone apps downloaded. 700,000 I think 700,000 was Facebook. There it is there. 695,000 is Facebook. Hours and hours, 13,000 hours of music downloaded. So we're doing more and more and more with our data requirements. So that means you as service providers have to provide more bandwidth for your customers and for yourselves. So now we're talking about fiber characterization. What is it? So one of my buddy field engineers was told to come to a customer site and do some fiber characterization. So he showed up with a sales guy. He had a big old kit, big old case, all the equipment necessary to do all kinds of tests. And the guy just said he wanted to do a power meter test. He just wanted to have a power meter and do some loss testing with the source. So fiber characterization, we have to be careful in the sense that it can mean different things to different people. So people do a loss test, they'll say, I characterize my fiber. So that's fine and dandy. When we typically say fiber characterization, what we're typically referring to is a whole suite of tests, some that you may or may not do. So in the old days, our traditional test was hopefully fiber inspection. We need to make sure our fibers are clean. Then we would do loss, one way or both ways. We would often do ORL for higher speeds, and then we do a OTDR. So our limiting factor was loss, was attenuation. Do we have small amount of loss in the span so I can transmit from point A to point B? Loss was the limiting factor. Well, now when we go to high speed, loss still applies, but really applies now for the limiting factor is dispersion. There's polarization mode dispersion, and there's chromatic dispersion. That's PMD and CD. So now with amplifiers and low loss fiber and everybody's handling the fiber better, we have less loss, we don't have bends, we can typically take care of loss by putting amplifiers on there. But when we go to high speed, all of a sudden we have to worry about dispersion, and that becomes a new limiting factor. So that's what the focus is today, is PMD and CD. So you may have been doing fiber for 5 years, 10 years, 20 years, a long, long time, and splicer person, CO person, field person, construction, and we've had an OTDR, we've had bidirectional loss testers, we've had inspection devices, and we've never had to do PMD or CD. So why do we have to do this now? And typically it's for high speed, which is 10 gigabit or above. So the example I use is an old wooden covered bridge. If we see those in some of our neighborhoods out in the rural communities, they're 100, 150, 200 years old. They're very old bridges. They were designed for the time for a horse and buggy. If you want to drive an 18-wheeler over that, you better do some more tests, because even on a cement bridge with steel and cement, there's often a weight limit saying how heavy the truck can be. So if you have old fiber that I would equate to an old wooden covered bridge or a small weak cement bridge, when you go to this higher bandwidth, this heavier load, you have to do new and different tests. So the fiber was fine 5, 8, 10, 12, 15, 20 years ago when it was put in for the current day applications at the time, but now as we go to high-speed stuff, we have to run these new tests. So the focus is on PMD and CD. I will cover some of the high points on some of the older tests, because we go out to do PMD and CD, but we see horrible bends, dirty connectors, big losses, bad splices. A lot of the old stuff still got to get fixed. Also commonly, many of us are used to, if we're a telco person or a CO person, we're used to the blue connector, the UPC connector, such as the Sam Charlie UPC or the Lima Charlie UPC. Now many times the manufacturers will force us to APC, the angled physical contact, whether you like it or not. And the reason for that is having an angled connector makes your back reflections about typically at least 20 dBs better. So your back reflections are 100 times improved. So when we go to 1 gigabit per second and then we go to 10 gigabits, the ones and zeros are 10 times closer to each other. So if you have reflections bouncing around, they become bit errors with them little ghosty bits bouncing all over the place. So it's common for us to get APC connectors now when we go to high speed, DWM, ROADM, or even just 10 gig or higher on one single channel. So you commonly have green in the network and you have blue. So green to green is a good connection. Blue to blue is good. Do not connect a blue to a green. 95, 90% of the time your network is not going to work at all. It might work on a very, very short span. But blue to green is not good. In the same way as your testers. If your tester is blue and your network is green, you just use a hybrid jumper to make sure you can make the connection. I also got to throw in the 30-second class in 2 minutes on fiber inspection. All the network stuff out there is supposed to last 25, 30, 40 years. So if we put cable in the ground or we put it on a pole, it's supposed to last a long, long, long time. The part that we touch is the connector at the very end. It's the most vulnerable port, but that is commonly the most neglected part of the network. So cleaning on shirts, hopefully this is all review right here, but a lot of folks got to have 2 or 3 or 4 times a hearing this, or they connect dirty, they cause permanent damage, they bring a network down. In the old days, I thought it was 3 days pay for bringing down a T1, which was 24 phone calls. Now, if we have one fiber, if you're in the CO or on a big backhaul or a long haul network, one fiber could be thousands and thousands and thousands of phone calls and potentially take down a multiple state area. So if you connect to a network with a dirty jumper, that could be either a resume generating event or a career changing event. So we do have to keep our stuff clean. This slide here in the lower left, a couple of tiny pieces of dirt touching that core. Our back reflections get 30 dBs worse. That's 1,000 times worsening, and we pick up 4.6 dBs of extra loss. In this picture number 3 here, you drop a fiber on the ground, it's easy to get it that dirty just by dropping it on the ground. And many of us don't realize it can cause permanent damage, but you can connect a fiber that is dirty and cause permanent damage. So here is an example of that. I have 3 pieces of dirt and a fiber. I can kind of see my core, which is one piece of dirt there, a dot at 5 or 6 o'clock. And if I connect this guy 1, 2, 3, 4 times, the big pieces of dirt explode. They're everywhere. The little pieces of dirt get stuck in the glass, and the core is completely covered. So basically your core is now blindfolded and may have permanent damage. Tapping a fiber with your finger makes it filthy. And now if I take that filthy, oily fiber connected to a clean fiber, the clean fiber becomes filthy. So in this case, I can see a ring at 200 microns. That represents the contact area. I call it the bubble or dome. The technical term for it is radius of curvature. So that shows the forces involved. It pushes the liquid out. So this is a good visual aid to show that if you connect a dirty fiber to a dirty or clean fiber, you may cause permanent damage. In the same way, if your windshield gets chipped, you can't clean it. If you permanently damage your fiber, you can't clean it. $40,000 test was sent back to us twice. Our technician cleaned it twice and sent it back. There was a little bit of permanent damage, but it was able to work. So both sides, male and female, need to be inspected. It's even more critical at the high speeds of 110 gig channel, 40 or 100 gig, or 40 10 gigs on one fiber, because there's a lot of zeros and ones that are close together. So dirt causes reflections and makes your ORL go worse. So our stuff needs to be clean if we're talking about dispersion. Because we're talking about dispersion, we're talking about high-speed traffic. So we say inspect before you connect. If it's dirty, you clean it. If you can't get it clean, you replace it. If it's clean, you don't touch it, you just connect it. So there's a 30-second review. But if you have folks working on the side of the house or out at some nodes or some enclosure boxes, a lot of times we have poor practices and we can get away with it in low-speed stuff. We can certainly make a low-speed circuit fail, but on high-speed circuits, it's even more critical. If you have any third-party people involved, if you're not doing your own characterization, or if you have contractors or you hire test equipment contractors to do testing for you, then you can require them to give you a picture of every fiber, so that way you verify that it's clean. And even though if they give it to you clean, if it's not connected, it can get dirty overnight. But if you have third-party workers, or even for your own workers, if you need documentation, it's nice to have a probe that documents that you started with clean fiber that passed against the international standard. If you've been working with a power meter for a long time, we have to know the difference between dB and dBm. A power meter is blind. You have to pick the wavelength. You have to have a reference, and you have to know the difference between dB and dBm. Your average power meter is going to do an automatic reference for you, so it's going to do dB and dBms for you automatically. So dB is a relative measurement. It's a comparison against a known start point, while dBm is an absolute measurement, dB milliwatts. So I use money as an example. If I take money from you, you don't know how much I took. But if I saw that you had 100, that's $100. That's 100 dBm. It's actual money. So in light, it would be dB milliwatts. The light transmits at X power. So that says a plus 5 dBm. Well, if you have $100 and I see that you have $80, $80 is a dBm. So the loss is 20 dBs. You don't physically see that 20. But because you went from 100 dBms, $100 to 80 dBms, $80, then you know your loss is 20, which is in dB. So when they're doing their loss test, make sure they know dBs and dBms. Their tester should do referencing for them automatically. So in this case, I have a jumper on my source. I have a jumper on my meter. I reference it out. Now it calibrates it. It references it. It ignores it. So I'm not including the loss of this jumper and these connectors. I'm just getting the loss on my span. Bends are important because we're transmitting in the C-band, the 1550 range. And them high wavelengths, 1550 and higher, do not like bends. So if you're using your OTDR, we got to find and get rid of those bends. The fiber normally is straight, no bends. So if you put a bend in it, that means the bend can get worse. A bend can go away, but it also means it can get worse. So typically, when you're doing your fiber characterization for high-speed traffic, if you have bends out there, you need to find them, locate them, and get rid of them. The other thing for you is some ORL. Our standards, if we're working with contractors or middlemen, or we're buying fiber, we're getting fiber, we're receiving for it, we do loss both ways, ORL both ways, and we do OTDR both ways. Your OTDR will give you ORL. It's a little bit less accurate than an optical continuous wave reflectometer or a continuous wave ORL meter. So I don't sway people. If you're hiring a contractor, you're probably going to require demand that they give you continuous wave ORL meter measurements. But if that was done originally a long time ago and everything is clean, if your OTDR shows good RL, then your ORL is good. So typically a CW ORL meter is off by plus or minus 0.5, and OTDR is off by plus or minus plus or minus 2. It's a difference of 1.5 dB. So if your network can't handle a difference of 1.5 dB in ORL, it's probably going to fail anyway. So I won't sway you one way or another. If you have an OTDR, always use it for ORL just to make sure that ORL is good. But it's commonly required that ORL has to have the continuous wave ORL meter in use. ORL is also a positive number. So an individual reflector is negative, but a ORL test gives us a positive number. So for ORL, we actually want a higher number. A plus 50 is better than a plus 40, which is better than a plus 30. But for individual reflection with the OTDR, a neg 50 is better than neg 40, which is better than a neg 30. A lot of times that we've been doing power meter and OTDR for a long time, we don't do ORL. The other thing for ORL is when we test these long haul spans for high-speed traffic, to go from point A to point B, both ends are connected. Well, if you're using an OTDR, many times your far end is not connected. So if you're on a short span, that open, especially if it's UPC, causes a high reflection, and that can hurt your ORL. So if you're using an OTDR and you're 5, 8, 10, 12 miles, feel free to plug in the far end to take that neg 14 to a neg 30, neg 40, or neg 50, and that can help improve your ORL by a couple of dBs. When you transmit traffic, I said you were connected at both ends. So if disconnecting at one end makes your ORL go bad, and that's not how you transmit, you can connect that far end to a source, a OTDR, or some other tester, or even a non-reflective terminator, and that can help improve your ORL if you're using an OTDR. There's also single-ended ORL, so even if you're using a continuous wave ORL meter just from one end, you may need to kill the back reflections on the far end. Launch cables, this applies to dispersion as well because we're often doing the OTDR. We're often on longer spans. So some folks will say I need a 50 meter, 100 meter, a 500 meter, a 1,000 meter launch cable. The point of the launch cable is to get the loss of the front end connector. So in our typical OTDR trace, we see these little spikes, and that's the reflection of the connector. Well, if you shoot a 2,000 meter pulse width, your spike is going to be 2,000 meters long. So if you're using a 1,000 meter launch cable and you have a 2,000 meter launch cable, your launch cable really isn't effectively doing anything for you at all. So if you go to longer spans, you would need a longer launch cable. We mentioned in past sessions there's mapping software. So we have a lot of people now working in fiber. If you can't analyze an OTDR trace because it's 50% science and 80% art, have the OTDR use mapping software and analyze it for you. And the other thing is with our OTDR, we can shoot a long pulse width. Maybe you need 2,000 meters to go 100 miles. And we can turn around and shoot a 3 nanosecond pulse width or a 2 nanosecond pulse width, and that lets you see everything in the building. So we have something called Smart Acquisition. That would allow you, even if you're shooting on a 120-mile fiber, just to use a 10-meter launch cable, because basically we're going to shoot 2 traces. So that's a review of our basic tests. If you have bends, bad connectors, horrible splices, dirty connectors, all that stuff's got to get fixed before PMD and CD apply. So PMD and CD is a limiting factor, but if you got an 8 dB bend out there, that's got to be fixed because that's going to kill your network. I'm going to open the lines to see if we have any questions. Hopefully most of that was review, but when we go to PMD and
All
CD,
participants are now in interactive talk mode.
all those tests still apply. We see folks have to fix a lot of stuff before they can worry about all the high-speed stuff. Any questions? If not, we'll keep rolling forward, and now we'll go into what we're really waiting for is the PMD and CD.
All participants are now in listen-only mode.
So on our old fibers, we did not do PMD and CD at 2.5 gig, 1 gig, OC12, OC48. So now we're going to be doing these for higher speed networks, which is typically OC192, 10 gigabit Ethernet, and a 40 gig or 100 gig or higher speeds, or something like a DWDM or ROADM. A lot of times we've been running slower speed traffic for a long time. So as we go to higher speeds, then we actually do need to run characterization on fibers that are currently having traffic on them. So when we go to OC192 and 10 gigabit Ethernet and above, dispersion does apply. OC192 is very intolerant of dispersion. On our older spans of OC48, dispersion has always been there, but the ones and zeros are spread out. So if the one is spread out and the one next to it is spread out, when they disperse, which means they spread, they don't bump into each other. But now when we go from 1 gig to 10 gig, the ones and zeros are 10 times closer, so when they spread out, they actually bump into each other and they cause a bit error. So most of this stuff is going to come from your network equipment manufacturer, Lucent, Ciena, Cisco, name them all. They'll tell you what they want the plant certified to. So many times they won't warranty the service until it's actually done. So after today, after talking about PMD and CD, if you were to meet with the manufacturer and they said they want these certain numbers or these particular set of specifications, you'd be able to discuss that with them. And we say there's two kinds of characterization. Typically the fiber is dark, we test it, and then we see that based on PMD and CD and our old test of loss ORL and OTDR, it's acceptable for high-speed traffic. The other one we call network characterization. We characterized that fiber a long time ago, so we may want to do a sanity check on PMD or CD. We put compensators in there, we put amplifiers in there, and prior to turning up the traffic and service, you might do a quick test again, and also for troubleshooting. So CD, I'm going to go over the basic definition, and that is different colors of light travel at different speeds. So if we draw 1550 as a 1 on the whiteboard, we just draw a bip. And that just represents, hey, the light is on, I see a digital 1. When we say it's 1550, we're doing 10 billion bits per second. It's actually not a true 1550. In this case here, I see some green, I see some yellow, I see some orange and red, and I see some blue. So basically this 1550 laser is a 1550 in the middle, but it's also a 1550.001 and a 1549.999. Well, when we travel down long fibers, the different colors travel at different speeds. So if we say this is a red, green, and blue, 3 colors that make up this 1 1550 peak or spike, as we go down the fiber, that red, green, and blue spreads out. So now that bit has spread, it has dispersed. So we started with high power, so now you can see it's smaller, so that's our attenuation, it's loss. Loss still applies, but what's new to us is the spreading of the bits. So it's pretty easy to understand, and even if we don't understand that, chromatic dispersion spits out a number. If you can operate a power meter, an OTDR, or a splicer, then you can operate a CD test. You turn in the number and you let the back office people or the engineers or designers do something with the number. So this is a little bit of a busy slide, but I'll try to keep it simple here. We have our basic fiber types, 652, G.653, and 655. And G.652 we call non-dispersion shifted fiber. That is typically SMF28 or SMF28E. It's your old standard single mode fiber. That is mostly what is in the ground. In the old days, we transmitted at 1310, so there was no dispersion at 1310. Then we started transmitting at 1550, so we had G.653 fiber. That's called dispersion shifted fiber. So we made zero dispersion happen at 1550. So here it says dispersion at 1550 is 0. Well, then when we went to do DWDM, if you put channels side by side, it actually caused network problems. So they created G.655. It's called non-zero dispersion shifted fiber. So now, instead of having zero dispersion at 1550, we have a little bit of dispersion, and that lets our DWDM work. So the numbers here say picoseconds. A picosecond is a trillionth of a second. So on old fiber, such as SMF28, G.652, which is mostly in the ground, we can expect 16 to 18 picoseconds per kilometer. So if you go 1 kilometer, 3,000 something feet, you'd expect to see 16 picoseconds of dispersion. That bit spreads out by 16 trillionths of a second. So if you go 50 kilometers, 30 miles, 50 times 16 is 800. So CD doesn't change over time, and if the fiber is the same, all SMF28, then you should expect on 50 kilometers of fiber or 31 miles to see 800 picoseconds of CD. If you have dispersion shifted fiber, G.653, you'd expect to be about 0, and if you have some non-zero dispersion shifted fiber, it'd be about 3 to 5, right? 5 times 50, you'd expect 250 picoseconds on 50 kilometers of fiber. And also these numbers, you can have the tester do the work for you, so you don't have to worry about picoseconds, you don't have to worry about kilometers. The tester is going to spit up the total number for you. So the good news for the service providers is that chromatic dispersion is fixable. We can compensate for it. We use a dispersion compensating fiber or a dispersion compensating module. A module will actually go into your network element device, and it compensates. So we said the colors travel at different speeds. We just put a different fiber type in there, and then that will let everybody catch back up. So the example of that is if you're going to race a Humvee and a Ferrari, you might pick a Ferrari. Well, out on the highway, the Ferrari is going to be much, much faster than the Humvee. It's spreading. It's dispersing. We're not driving down the road side by side. So if you're supposed to show up at the same time, that would be bad. So to slow that Ferrari down, we're going to flag him over, and we're going to put him on a dirt road. Now the Ferrari has got to go slow, and the Humvee can catch up. So that's what we're doing on the fiber. If one color is fast, we put some different fiber in there, and that lets the slow guy catch up to the fast guy. So we correct the spreading, we correct the dispersion that is on that span. So we turn in the number, and the design folks, the R&D folks, or the engineers, or the manufacturer in combination with the provider says, okay, we're going to compensate for CD. So now we'll go to polarization mode dispersion. A little bit harder to explain, but it's the same thing. The tester spits out a number, and you turn it in whether you can spell PMD. It's not that hard. But the reason why PMD appears is because the fiber is not perfectly circular, and that happens during the manufacturing process. Additionally, PMD can change over time because if we smush the fiber, we twist it, we stress it, we bend it, that changes the shape of the fiber, and that affects PMD. So we'll try to keep this easy, but if we get sunglasses, they commonly say that they're polarized sunglasses. So when we say sunbeam or sunlight, we think, I see one beam of light, I see the sun. Well, technically, it actually is the sunbeams and sunlights. And what that means is when we say there's a 1550 for a spike, we just draw that spike. So down here, I see a spike. But there's not actually one spike. There's many, many, many different spikes. So if you put your sunglasses on, you'll see stuff change color. A pink tile can become blue. So basically, that sunlight is made up of multiple beams, and those sunglasses are blocking some of them beams. So if you have 3 beams that make something yellow, and your sunglasses block one of the beams, and all of a sudden it changes colors. So to try to keep it simple, when we say there's a 1550, we say there's actually many beams or many poles. In this case here, we're just going to do 2. I got one here, a V2, and one here, a V1. Well, if the fiber was perfectly circular, we would go down, take the same path, and we come out together. But the fiber is not perfectly circular during the manufacturing process. So it would be like me and you going in a tunnel and walking side by side at the same speed. Well, if your side of the tunnel is perfectly flat, and mine goes up, down, left, and right, and twists and has hills and goes from side to side, you're going to get to the end of the tunnel faster than I because I took a longer path. So based on the physical shape of the fiber, that makes these different beams spread out. So once again, the example is glasses. It's not just sunlight, it's sunlights. There's multiple beams, and the glasses block it. When we buy our suntan lotion, it says it blocks UVA and UVB. So that's ultraviolet rays A and ultraviolet rays B. So even though it's sunlight, there is 2 beams right there, and that suntan lotion is blocking those 2 beams. So it's the same way with our light when we travel on the fiber. It's just not one beam. It's actually multiple beams, hundreds of beams, and they take different paths. They take different routes. That makes them spread out, and they go all over the place. There is also a new method out called one-ended PMD. While historically PMD has always been 2-ended. So if you look at one-ended, if you ever find out about that, a lot of limitations in that, so you need to look very closely. Long spans will automatically get it booted, and accuracy would get it booted. Amplifiers would get it booted. You commonly need a second person at the far end. So if you take a look at one-ended PMD and one-ended CD, you need to be very careful. 2-ended PMD and CD testers are all pretty accurate. They use the same standard. If you compare a one-ended tester to a 2-ended tester, you should find some major discrepancies. Another test that we do when we do our CD and PMD tests is we use a spectral attenuation test, and that's a loss test, but it's using a broadband source. So instead of testing loss at 1310 and 1550, we test it in the C-band or L-band or even a little bit more, because you have all these channels on DWDM and ROADM, and now the back office people can get lost across the spectrum. And that helps them tune their network, whether it's automatically or manually, to make sure all the channels have the same power. So you can use an attenuation profile test, even if it's not required. If it's not required, I like to use it as a sanity check just to make sure that my loss across the span is still good. So now we'll talk about typical results and expected results and pass fails. So the PMD max depends on the fiber type, the traffic type. OC192, you're allowed 10 picoseconds. For 10 gigabit Ethernet, you're allowed 5 picoseconds. Now for PMD and CD, even if the fiber is 10, 15, 20 years old, I bet it passes 90% of the time. Old fiber is 1983, and the next old fiber is 1993. So a lot of the fiber is in the ground before 1993 anyway. So if you test 12 fibers, 11 of them could pass, but if the one guy has been squished, bent, the weight's in the cable underground or on the pole, then you can get one bad fiber and you have to tag it out. It's not acceptable for it. When you go over to CD, here's a max for OC192 and a max for 10 gig Ethernet. It says the max for 10 gig Ethernet is 738 picoseconds. Well, I said if we're on old fiber, which is what is mostly in the ground, you expect about 16 picoseconds per kilometer. So if you go 50 kilometers, which is 31 miles, you're going to have 800. So if I'm on a 30-mile span, I expect 800 picoseconds of CD. You're already above the allowable amount. So on most spans, the manufacturer is going to have you compensate. They don't necessarily have to knock it down from 738 to 0. Oops, we are at 800. But they might knock it down from 800 to 600 or 800 to 400. So if you turn in your CD results, the manufacturer or your own engineer and R&D and design folks will say, okay, we need to put a compensator here or here to reduce the speed or to reduce the dispersion. So we got the basic definitions. Most of the fiber characterization is old stuff, inspection, ORL, loss, OTDR. The new stuff is CD and PMD. So can we do these tests? Who should do them? Should I pay somebody? Should I rent the stuff? So that's what we'll talk about now. Now we got the basic definitions. As we see more and more requirements for PMD and CD, what do we do about it? Just a few years ago, we might have to do PMD and CD once per year, so we might hire somebody to do it, or we might rent a tester. So polarization mode dispersion, chromatic dispersion, I try to give the 30-second definition in 2 minutes. It still can be tricky, but for our tester, PMD and CD, we have a test auto button. So the OTDR is auto, PMD is auto, CD is auto, bidirectional loss is auto, bidirectional ORL is auto. The other thing is that we use a script. So you just say, I want to run these tests, answer yes or no questions, and the tester runs all these tests for you automatically. So you might not be able to spell PMD. What I said might not have made any sense, but I think a PMD test is easier than a power meter because it auto-references, it spits out a number, there's no dBs, there's no dBms. My world record is somebody called and said I have to go do PMD and CD testing tomorrow and my ORL, loss, and OTDR test as well. I didn't have a tester in front of me. I talked to him for an hour. Then I didn't hear from them for 2 days, so I just said, hey, did you get all your tests done? And they said, yeah. If we go face-to-face, we'll typically schedule about 3 hours, a little bit of hour of theory, do a couple of stuff on the tabletop, and we go out in the field, and I don't touch anything. I just watch the folks, and they start cranking out these tests. Once again, we know our typical results. PMD pass most of the times. CD on a lot of fibers is going to fail because it's predicted. We know what it should be. We don't technically fail CD because we can fix it. Today, PMD, we do fail it. We don't use it for 10 gig. And we go to 100 gig, and we'll talk about that a little bit today. There is a potential way to fix or compensate PMD as well. But if we're doing your typical 10 gig system today, if PMD is high, we got to tag it out. My buddy Steve calls it bandwidth mining. Find the ones that are good and use that for your high-speed stuff. The other stuff can't be used, or it's only used for lower speed traffic. Typically, if we're going to 10, 40 gig, or 100 gig, even if it's brand new fiber, the tests are often required by the manufacturer. And the other thing is just for documentation purposes, I got 5 miles of fiber here, 5 miles here, 5 miles here, 5 miles here. We tend to do the tests so we have the documentation when we go from 10 gig to 40 gig to 100 gig to multiple fibers on one channel. And commonly, it's a manufacturer who requires it, and commonly the fiber is not brand new. Commonly the fiber is old. PMD and CD are based on distance, so I've also seen the flip side. If your fiber is 1 mile long, and that was an entire span, you don't really need to test for CD because it's not a long enough distance for it to impact the traffic. But when we go to ROADM and DWDM networks in multi-state areas and huge metro areas, we're talking about a multi-million-dollar project, then sometimes we see the opposite of, oh, we don't got to test, we don't got to test. All of a sudden we say, we got to test everything. And that's because somebody's putting their signature on a multi-million-dollar project. We get a little nervous. In the old days, fiber characterization was pretty expensive. But if you look at the cost of hiring somebody can be about $3,000 to $5,000 a day, and for a week, 20 to 25 grand per week is not that bad. The other thing about it is if they're local, you might get a better price because they don't got to fly. A lot of folks who do this for a living fly across the country. They fly to other countries, and then once they get there, a lot of their time is just spent driving in a car. So you're basically paying $3, $4, $5 grand a day to have somebody drive in the car. So at 25 grand a week, it doesn't take too many weeks before you bought yourself a new tester. In addition to buying testers, the rental companies have the gear on the shelf that you can rent for a short time. I also think that's expensive, but if you don't have a whole bunch to do, that's a viable option. And the other scenario is leasing a unit. Apparently there's tax benefits, there's accounting benefits, where you get the gear, you own it later on, but it's another way to potentially spend money. So if you only got to do one per year, you might pay somebody to do it, or you might rent the gear, but as we get more and more and more testing out there, then all of a sudden it's certainly going to make sense to do your own testing, and then you'd either buy it up front or you can lease it. So if you do a whole lot of spans, it definitely makes sense to have your own equipment or lease the equipment. You can contract it out. If you do it to the network equipment manufacturer, right, they want to sell you equipment so you can have huge, powerful, fast, protected networks. That's where the money is. So they want their engineers doing that kind of stuff. They don't want them out testing. Some of the NEMs will actually hire us to go do the work, or they hire third-party contractors anyway. So if you do the NEM, it's safe with them. Commonly, they're very busy. They can be a little bit slow, and they can be very expensive. And you can pay the third party. We know guys who do this for a living. And it just comes down to, once again, the quantity. How many fibers am I going to test? So by using our script, our full automation, we automatically store the results, and we automatically create a little summary report. So if I'm new to PMD and CD, it's intimidating, then the summary report, usually if you turn in the traces in the summary report, you can get away with it, and that's pretty good. So I'll give you an example here. This is a report that was automatically created for me. I tested 3 fibers. I have my ORL at 1310 and 1550. I have my loss at 1310 and 1550. I have my distance of the fiber. I have my PMD. I have my PMD coefficient. I have my attenuation profile. And I have my total CD, dispersion at 1550. With a 50-kilometer span, we expect to see 800, and sure enough, there's 800. So many times we turn in the summary report and the actual traces. That suffices, which means the technicians have to do no work on their PC. And that's what we talked about right here. Everything is stored automatically, and everything is put into a summary report. If you want to do a detailed report that includes bidirectional splices, OTDR both ways, then we have PC software as well. So if we want to do OTDR one way, CD, PMD, and AP, we connect to the tester once. That's because we have a switch. And in about 2.5 minutes, we can run all those testers, automatically save them, and automatically have a summary report. So this is what I'm talking about with switch and automation. Here there's a switch on the T-Bird. It's connected with little tiny 9-inch jumpers. And when I put this guy into my hard case, those mini jumpers remain connected, so my optics are always protected. And then here on this page, I select what test I want to run, put in my job info, and I answer yes, no questions. And I'll actually do this as live as well, because I can do CD, PMD, AP, and OTDR in just about 2 minutes. And so many times you have bidirectional loss testers. The contractor did it a long time ago. You did it a couple weeks ago. But if you have to do bidirectional loss and bidirectional ORL, then we have two main frames, a T-Bird 8000 on one end, T-Bird 6000 on the other. Once again, we only connect the fiber under test once because we have a switch. The T-Bird 6000 module is an OTDR, bidirectional loss, bidirectional OTDR, and dispersion source. So with a traditional two-ended tester, 7 connections would be required, while we only need 2 connections. And once again, over on the 8000, our dispersion module and OTDR are protected because we can put the T-Bird 8000 in the hard case with the little mini jumpers on. So I'll pull this up live. I select the test I want to run. I hit start, and then everything starts for me. So in this case, we got fibers 4, 5, 6, 7, 8, so I can see a summary of what's been going on. So without even going anywhere, I can see my loss, ORL, distance, PMD, and CD all from one page. So I'm going to open the lines up, and I'm going to go ahead and start some tests by using the script.
All participants are now in interactive talk mode.
So here I see a T-Bird 8000. And we're going to run a PMD and CD test. So here on my script page, my automation page, I select the test that I want to run. Notice I could have bidirectional loss and bidirectional ORL.
No,
I got my CD.
Nothing earth shattering for me.
I got my PMD. I've run some tests. So here's my loss, ORL, loss and ORL at 1310 and 1550, my distance, my PMD, and my CD. You can also see repeatability, which also is very important when you're running PMD and CD. ORL, exactly the same. Loss is a difference by 0.04 at 1310, exactly the same at 1550. Distance exactly the same. PMD different by 1/100th of a trillionth of a second, and CD 833, 833. So once you pick your test, put in your job information. We just hit start. And prior to doing this, right, PMD was auto, CD was auto, OTDR was auto. If you do bidirectional loss, it's auto. So do you want to run OTDR? I hit yes. It's going to auto configure. You can have your own configurations in there, but auto configure ensures we get a good trace. It's also going to give us a connection check. My box is getting old, and my testers have been shared. They're getting old, so instead of having a great connection check, I was just about average. 30 miles of fiber. It's running a 20-second test at 1550. If you had to run an exact time, then you could go ahead and say, you know, I got to run this for 47 seconds or 1 or 2 minutes. It's going to turn around and run the second wavelength. So it's going to auto-configure. There's my connection check at the other wavelength. You plug in dirty, it's going to be bad. It's picking 20 seconds at 1310. This check source. So my far end is a handheld source. It's the PMD and CD and AP source. So all I have to do is turn the PMD source on. I hit yes. It's going to run me a PMD test. We said for 10 gigabit Ethernet, we're allowed up to 5 picoseconds. Most of the times it's under 1, it's under 2, it's under 3, right? 90%, depending on the age of your fiber, it passes most of the time. I'm on 30 miles of fiber. There's my bar graph of power. I still got about 75% of my power left. So we can go extremely far distances. PMD is done. It spits out a number. Now I turn my AP source on. Right, the PMD and CD and AP are all in the same module. I hit yes. It's going to run an AP test. So this uses a broadband source. It's not lost at 1550. It's lost at 1550, 1549, 15 whatever. And now I turn on my CD source. I hit yes. And it's going to run chromatic dispersion. So just by doing PMD and CD and OTDR on auto, once again my CD, I'm on 30 miles of fiber. I still had about 80% of my power left. Now we're done. So do I go to my next fiber? Do I retest this fiber or do I stop? So I'm going to go ahead and hit no. I have alarm set, so if my distance is correct, my ORL is good at both wavelengths, my loss is good at both wavelengths, my PMD, right, it changed by 0.02 trillionths of a second, CD changed by 1 trillionth of a second, then without even going and looking at one results page, I know we're good. And then also, if my loss was higher at 1550 than at 1310, I would know that I have a bend. But if I press my results button, I can go back and look at individual results. Here's my OTDR trace. Here's my PMD. It does all the math for me, right? What is all the stuff up here? That's calculus. But look at this number right here. Because we have alarm set, big old giant number, 0.5. So that certainly passed for 10 gig Ethernet and higher speeds. Attenuation profile. At 1550, we were on 50 kilometers of fiber. So my profile was 0.19. 9.8 dB of total loss. That sounds about right. That makes sense. Chromatic dispersion at 1550. We went 15 kilometers, so we said we should see 16 to 18. We had expected about 800. So there's my coefficient. It's a 16.4. Total is 832. And once again, if I don't know any of this stuff, it's all automatically stored. Back on my script page, it tells me all my stuff is being stored into my disk demo folder. So if I go to my file hard key, there's my demo folder. It created, my cable ID was called cable. So here's my AP results, my PMD results, my CD results, my OTDR 1310, my OTDR at 1550. And here's my summary report automatically stored as a TXT and a CSV. If I go to my setup page, if I look at the OTDR, in the upper right, the OTDR has a test auto button. PMD has a test auto button. AP has a test auto button. CD has a test auto button. So if I do auto, and even if you did bidirectional loss, bidirectional ORL, I set them all up in auto. For some of the tests, you do have to do a reference, right, if you're doing a loss test. I go to my script page, pick the test that I want to run, and then I hit start, and now I'm running all these tests, automatically creating a report and automatically storing them. So this is just a way of showing that they gave a basic definition of PMD, what we expect to see, what's good and what's bad. But a PMD and CD test shouldn't be that complicated or shouldn't be that hard, because it's just going to spit out a number whether you know the basic definition or not. So we've gone over the definitions, what we'd expect to do, why we have to run the test, what are the typical pass-fail results, can we run these tests, and that's why I wanted to do the demo. If I could put auto, and run 1310, 1550 OTDR, CD, PMD, and AP, I think it was under 2.5 minutes, maybe close to 2 minutes, then it should be feasible that, okay, my folks can do this in the field, because it's not as hard as they might think. And instead of having to pay somebody $3 to $4 to $5 grand a day, you can do the test on your own. So do we have questions on fiber characterization, either the newer stuff such as CD or PMD, or the older stuff? Or do I need to administer the written test now?
Mike,
Please
Dr.
administer test.
Here. How you doing this morning? Got a quick question.
Alrighty.
Got a quick question for you, Mike. The older fiber that you refer to, I have fiber that was placed in 1988, first generation, single mode. What's the likelihood of it being able to pass the PMD testing?
Okay, so 1988,
Yeah.
that's kind of old, right? 12 plus 14, 25-ish years, 26 years. But for us, really old fiber is 1983. So in 1988, you can expect to pass, but if I was doing some newer fiber, if I tested 12, I might have all 12 pass. If it was just a little bit old, or even if it was new, because one of them got messed up, it's smushed a little bit, its aerial and it's bent, 11 out of 12 pass. So if you had a cable of 12 or a big old cable, you're going to have plenty of good fibers. But based on the age, if all my new ones, like I just shot 30 miles of fiber and I had a 0.5 for PMD, you might get some higher numbers and you're probably going to have some fail. But even at 1988, it just should make you worry that, yeah, I got to do PMD because that stuff is 25 years old. I still expect plenty of them would pass for you to be able to use the fiber, but I also would expect that you'd see some failures, either low failures or high failures. For CD, it's going to be the SMF28. So if you went 30 miles, you're going to have 800 picoseconds. But remember, that doesn't fail per se, because you can go to the manufacturer and say, hey, I got 30 miles and I got 800 picoseconds, and they're going to say, oh, I'll put a compensator at the beginning, in the middle, or at the end, and we're going to knock it down from 800 to 400. So CD, you know it's going to be high, but it's fixable. And PMD, you're going to have some failures, but even at 1988, you still be able to get some out there that are going to pass and allow you to do 10 gig or DWM.
Thank you.
Oh, also, I didn't mention resources. This is webinar number 4. So in the past, I offer resources. I claim I'm at 100%. If you ask for something, I either sent you the hard copy, the soft copy, or both. So in this one, we have a fiber characterization poster. So if you mention what PMD is, what a typical number is, and what's a good pass-fail, and we mentioned CD, and we mentioned a lot of this stuff, we have it available in a poster, so it's just nice to put up on a wall when we're going to 10 gig E. What's typical acceptance for that, or what should my expected values be? That's a nice poster. And if you want to get into the details, for we did Fiber Basics, our first book was Fiber Basics. So I can send it as a soft copy or a hard copy. For the hard copy, there's a volume 2. So instead of talking about loss and inspection and OTDR, now it's going to go into the weeds on chromatic dispersion and polarization mode dispersion. So for a CO tech or a FEO tech, they might find a poster useful, but if you're a manager, back office engineer, R&D, or a data or network person, then the book can handy, because I gave the 30-second class in 2 minutes. Sometimes you're going to talk to that Lucent guy or Cisco guy. You might need more information, and that book's available as a hard or soft copy. So if you need those references, there's my email. Usually I take about 1 or 2 weeks, so I get all the requests. I do the soft copies pretty fast. Then I get all the hard copy requests, and I go to the fulfillment center, and I have those mailed out via hard copies. I'll stay on the line for a couple of minutes. If you'd like to ask some questions when there's less folks on the line, I do thank everybody for attending. Next session, 100 gig and ROADMs. Thank you for your time. Happy week.
Thanks, Mike.
Everybody. Anybody else have any questions as the lines have thinned out? I'm going to go ahead and end the session. I will be sending up the follow-up email, right? So you'll have the recorded link. I'll mention the resources available, and I'll mention that 5th webinar, which is going to be 100 gig in ROADM. Thank you, everybody.